Welcome back to another peaceful journey through the cosmos designed to help you drift into restful sleep. I'm your host Atlas Reed, and tonight we're venturing into the realm of the universe's most extraordinary musicians, neutron stars. These cosmic giants, no larger than a city yet containing the mass of our entire sun, create symphonies of radio waves that pulse across the galaxy with clockwork precision. We'll explore how these stellar remnants transform into cosmic lighthouses, their magnetic fields billions of times stronger than Earth's, and the fascinating physics that makes them sing their ancient songs across the void. If you enjoy these peaceful explorations of the universe, please consider giving this video a thumbs up and subscribing to join our community of cosmic dreamers. And here's something fun for you tonight. In the comments, tell me what everyday object you think would make the most interesting sound if it were spinning as fast as a pulsar. I'm curious to see what you come up with. Alright, let's dive in. To understand how neutron stars create their celestial music, we must first witness their dramatic birth. When a supermassive star with an initial mass greater than about 8 times that of the Sun begins to die, it forms a red supergiant before exploding as a supernova. This explosion is one of the most violent events in the universe, releasing more energy in seconds than our Sun will produce in its entire 10 billion year lifetime. But within this cosmic violence lies the creation of something extraordinary. When the star's core collapses during the supernova, gravity becomes so intense that it crushes protons and electrons together, forcing them to merge into neutrons. Imagine taking all the mass of our Sun and squeezing it into a sphere only 12 miles across. The enormous density of a neutron star means a teaspoon of neutron star material would weigh 10 million tons. To put this in perspective, a normal-sized matchbox containing neutron star material would have a weight of approximately 3 billion tons. This process creates matter so dense that it exists nowhere else in the observable universe. The material becomes what physicists call degenerate matter, where the normal rules of physics as we know them begin to break down. Picture trying to fit all the people on Earth into a single city block, and you begin to approach the level of compression occurring inside these stellar remnants. During this collapse, 2 crucial properties are preserved and intensified. First, the original star's rotation speeds up dramatically, much like a figure skater pulling in their arms during a spin. A star that once rotated every few weeks might become a neutron star spinning hundreds of times per second. The fastest spinning neutron star on record, found in a globular cluster of stars located around 28,000 light-years from Earth, spins around 716 times per second. Second, the star's magnetic field becomes concentrated into an area millions of times smaller, amplifying its strength to incomprehensible levels. Neutron stars have exceptionally strong magnetic fields around them, often billions or even trillions of times stronger than Earth's protective magnetic field. To visualize this, imagine Earth's gentle magnetic field, barely strong enough to move a compass needle, amplified until it could lift a car from miles away. These 2 properties, ultra-rapid rotation and incredibly powerful magnetic fields, work together to transform the neutron star into something remarkable, a cosmic beacon that sweeps beams of radiation across space with the precision of an atomic clock. The neutron star's magnetic field acts like a funnel, channeling charged particles from its surface into narrow beams that shoot out from its magnetic poles. As the neutron star spins, these beams sweep across space like the rotating beam of a lighthouse. When one of these beams happens to point toward Earth during its rotation, our radio telescopes detect a brief pulse of radio waves. This creates the rhythmic pattern that gives these objects their name, pulsars, short for pulsating stars, though they are not actually pulsating at all but simply rotating. The birth of each neutron star represents a cosmic recycling program of extraordinary proportions. The heavy elements forged in the original star's nuclear furnace are scattered across space by the supernova explosion, eventually becoming the building blocks for new stars, planets, and perhaps even life itself. Meanwhile, the collapsed core continues its eternal dance, spinning and pulsing, creating a cosmic metronome that can keep more accurate time than our most precise atomic clocks here on Earth. Understanding how neutron stars create their signature pulses requires examining their remarkable internal structure and the invisible architecture of their magnetic fields. These objects are far from simple. They are among the most complex and exotic structures in the universe, with physics that pushes the boundaries of our understanding. The combination of intense gravity, high temperature, and extreme density makes neutron stars like nothing we can produce on Earth. At their surface, gravity is so strong that if you could somehow stand there, you would weigh about 1 billion times more than you do on Earth. The surface itself is thought to be a crystalline lattice of atomic nuclei, creating what might be the strongest material in the universe, trillions of times harder than diamond. Beneath this surface lies a landscape that defies imagination. The outer crust contains nuclei arranged in a crystal lattice, immersed in a sea of electrons. As we journey deeper, the density increases so dramatically that normal atomic nuclei begin to merge and elongate into structures that physicists poetically call nuclear pasta, forming shapes that resemble lasagna sheets, spaghetti strands, and gnocchi balls, depending on the precise conditions. The core of a neutron star remains one of physics' greatest mysteries. Here, matter exists in forms that we cannot replicate or fully understand. Some theories suggest the presence of exotic particles that exist nowhere else in the universe, strange quarks, hyperons, or even more exotic forms of matter that challenge our understanding of the fundamental building blocks of reality. But it is the neutron star's magnetic field that creates the cosmic music we observe. Pulsars have very strong magnetic fields which funnel jets of particles out along the two magnetic poles. These accelerated particles produce very powerful beams of light. Often, the magnetic field is not aligned with the spin axis, so those beams of particles and light are swept around as the neutron star rotates. Picture a bar magnet spinning inside a globe filled with charged particles. The magnetic field lines stretch from one pole to the other, but they are not aligned with the rotation axis. Instead, they are tilted at an angle, creating a complex, twisted structure that rotates with the star. This misalignment is crucial because it creates the lighthouse effect that allows us to detect these objects from across the galaxy. The magnetic field acts as a cosmic particle accelerator. A gamma-ray pulsar is a compact neutron star that accelerates charged particles to relativistic speeds in its extremely strong magnetic field. Near the magnetic poles, particles are accelerated to nearly the speed of light, creating intense beams of radiation that extend far into space. These beams are not simply points of light, but rather complex cones of radiation that include radio waves, optical light, X-rays, and gamma rays. The radio waves that we detect on Earth are just one small part of this electromagnetic symphony. The beams are so narrow and intense that they can remain detectable across thousands of light years, like cosmic searchlights cutting through the darkness of space. The precision of these rotating beams is extraordinary. Some pulsars maintain timing accuracy that rivals or exceeds our best atomic clocks. This reliability comes from the neutron star's immense rotational inertia. Once spinning, these objects resist any change to their rotation with tremendous persistence. Their enormous density means that even tiny changes in their structure or magnetic field take enormous amounts of energy to accomplish. The magnetic field structure itself is dynamic and evolving. Over millions of years, the field gradually weakens as energy is radiated away, and the pulsar's rotation slowly decreases. This creates an evolutionary sequence where young, rapidly spinning pulsars with strong magnetic fields gradually age into slower, quieter objects that eventually fade from our ability to detect them. The cosmic music of neutron stars manifests most clearly in the radio waves that sweep across our galaxy, creating patterns of extraordinary beauty and precision. Pulsars are magnetized neutron stars that appear to emit periodic short pulses of radio radiation with periods between 1 and 4 milliseconds and 8 and 5 seconds. This range encompasses a remarkable variety of cosmic rhythms, from rapid-fire drumbeats to slow, stately pulses that mark time like a grandfather clock in the cosmos. The mechanism behind this radio emission remained a mystery for decades after the first pulsar was discovered in 1967. In 1967, shortly before the discovery of pulsars, Franco Pacini suggested that a rotating neutron star with a magnetic field would emit radiation, and even noted that such energy could be pumped into a supernova remnant around a neutron star, such as the Crab Nebula. Recent research has finally begun to unravel this cosmic mystery. The wobbling electric fields in the presence of the pulsar's powerful magnetic fields then result in electromagnetic waves that escape into space. Using plasma simulations, the researchers found that these electromagnetic waves match radio waves observed from pulsars. This breakthrough helps us understand how the immense magnetic fields and rapid rotation work together to generate the radio signals we detect. The process begins in the neutron star's magnetosphere, a region of space dominated by the star's magnetic field. This invisible structure extends thousands of miles into space, creating a complex playground for charged particles. As the neutron star rotates, it drags this magnetic field with it, creating electric fields that accelerate particles to incredible speeds. Near the magnetic poles, conditions become extreme. The rotating magnetic field creates gaps where particles can be accelerated to nearly the speed of light. As these relativistic particles spiral along magnetic field lines, they emit synchrotron radiation across the electromagnetic spectrum. The radio waves we detect are created through a complex cascade process, where high-energy particles create pairs of electrons and positrons, which in turn produce the radio emission through collective plasma effects. The resulting radio pulses carry detailed information about their journey through space. As radio waves travel from the pulsar to Earth, they encounter the thin plasma that fills interstellar space. This plasma causes different radio frequencies to travel at slightly different speeds, creating a phenomenon called dispersion. Lower frequency radio waves arrive at Earth slightly later than higher frequencies from the same pulse. By measuring this time delay, astronomers can calculate exactly how much plasma the radio waves encountered on their journey, providing a direct measurement of the density of interstellar space. This technique has revealed the structure of our galaxy's interstellar medium in exquisite detail, showing bubbles of hot gas blown by stellar winds and the aftermath of ancient supernovae. The radio signals also reveal the pulsar's motion through space. As the neutron star moves toward or away from us, the Doppler effect shifts the arrival time of pulses, allowing astronomers to measure velocities with incredible precision. Some pulsars are moving through space at hundreds of miles per second, kicked into motion by the asymmetric explosion that created them. Perhaps most remarkably, the timing of pulsar signals is so precise that they can be used as cosmic clocks. A millisecond pulsar is one with a rotational period between 1 and 10 milliseconds, or from 60,000 to 6,000 revolutions per minute. These rapidly spinning objects maintain their rhythm with such accuracy that they can be used to detect gravitational waves, minute ripples in spacetime itself that cause tiny changes in the arrival times of pulsar signals. The radio symphony of pulsars thus provides us with a window into some of the most fundamental aspects of physics and astronomy, from the structure of matter at nuclear densities to the nature of space and time itself. The magnetic fields of neutron stars orchestrate some of the universe's most spectacular phenomena, creating structures and processes that exist nowhere else in nature. These fields are not static entities but dynamic, evolving systems that shape the space around the neutron star and control the flow of matter and energy in ways that continue to astound astronomers and physicists. To appreciate the scale of these magnetic fields, consider that Earth's magnetic field, which protects us from harmful solar radiation and guides compass needles, measures about half a Gauss at our planet's surface. A typical neutron star's magnetic field ranges from 1 billion to 1 trillion Gauss, with some exotic objects called magnetars reaching fields of up to 1 quadrillion Gauss. At such intensities, the magnetic field contains enough energy to power our sun for millions of years. These fields create a complex three-dimensional structure around the neutron star called the magnetosphere. Unlike Earth's relatively simple dipole field, which resembles the pattern around a bar magnet, neutron star magnetospheres are twisted, dynamic regions where the normal rules of physics are pushed to their limits. The rapidly rotating magnetic field drags plasma along with it, creating currents that flow along invisible field lines like traffic on cosmic highways. The interaction between rotation and magnetic field creates distinct regions within the magnetosphere. Close to the neutron star, within the light cylinder, a theoretical boundary where the rotational velocity would equal the speed of light, the magnetic field forces plasma to rotate with the star. Beyond this boundary, field lines stretch and reconnect, creating open zones where particles can escape into space. At the magnetic poles, the field lines converge and create natural particle accelerators. Here, the combination of the strong magnetic field and the electric field generated by rotation creates gaps where particles gain enormous energies. Electrons and positrons are accelerated to speeds approaching that of light, creating cascades of secondary particles through interactions with intense gamma rays. The magnetic field also controls how matter falls onto the neutron star. In binary systems where a neutron star orbits a companion star, material from the companion can be captured by the neutron star's gravity. However, this material cannot fall directly onto the surface. Instead, the magnetic field funnels it toward the magnetic poles, creating hot spots where the infalling matter crashes into the neutron star's surface at tremendous speeds. This process creates some of the most energetic phenomena in the universe. As matter accelerates toward the neutron star, it heats up to temperatures of millions of degrees, emitting X-rays and gamma rays. The hot spots at the magnetic poles create beams of high-energy radiation that sweep across space as the neutron star rotates, much like the radio beams but at much higher energies. The magnetic field structure is not permanent but evolves over time through several mechanisms. All pulsars slow down gradually as they age. The radiation emitted by a pulsar is jointly powered by its magnetic field and its spin. As energy is carried away by electromagnetic radiation, both the rotation rate and magnetic field strength gradually decrease over millions of years. Some neutron stars experience sudden changes in their magnetic field configuration through events called magnetar flares. These are thought to occur when the neutron star's crust suddenly cracks under magnetic stress, allowing field lines to reconnect in a new configuration. The energy released in these events can be detected across the galaxy, briefly outshining all other X-ray sources in the sky. The magnetic field also plays a crucial role in the neutron star's long-term evolution. Young pulsars with strong magnetic fields eventually evolve into millisecond pulsars through a process of magnetic field decay and spin up by matter accretion from a companion star. This evolutionary pathway connects the rapid pulsars we observe to the slower, older objects that represent their eventual fate. The rhythmic pulses of neutron stars have transformed our understanding of time itself, creating cosmic chronometers that surpass even our most precise atomic clocks in their stability and accuracy. These celestial timepieces provide insights not only into the nature of neutron stars themselves, but also into fundamental physics and the structure of the universe around us. The discovery that pulsars could serve as extraordinarily precise clocks came as a surprise to early astronomers. The first pulsars were discovered through their extremely regular pulses of radio waves, but it took time to realize just how regular these signals could be. Some millisecond pulsars maintain timing accuracy that allows astronomers to predict the arrival of pulses years in advance with precision measured in microseconds. This extraordinary regularity stems from the neutron star's immense rotational inertia. The star's incredible density means that once it is spinning, enormous forces are required to change its rotation rate. Think of trying to slow down a massive flywheel versus stopping a spinning coin. The neutron star's rotation is so stable that even earthquakes on its surface, involving the sudden rearrangement of matter weighing as much as mountains on Earth, produce only tiny, measurable changes in the pulse timing. These timing variations tell fascinating stories about the neutron stars themselves. Occasionally, a pulsar will suddenly speed up slightly in an event called a glitch. These glitches are thought to occur when the neutron star's crust, which rotates slightly slower than its interior, suddenly cracks and readjusts to match the faster rotation of the core. The resulting change in pulse timing provides direct evidence of the neutron star's internal structure and the exotic physics occurring within. The precision of pulsar timing has opened up entirely new fields of astronomy. By carefully monitoring the arrival times of pulses over years or decades, astronomers can detect incredibly subtle effects. When a pulsar is part of a binary system orbiting around another star, the gravitational field of the companion causes small but measurable changes in the pulse arrival times as the pulsar moves toward and away from Earth in its orbit. These orbital measurements have provided some of the most stringent tests of Einstein's theory of general relativity. The first indirect evidence for gravitational waves came from observations of a binary pulsar system, where the two stars are spiraling inward as they lose energy to gravitational radiation. The rate of orbital decay matched Einstein's predictions with remarkable precision, earning the discoverers a Nobel Prize and confirming one of the theory's most subtle predictions. Pulsar timing arrays, networks of telescopes monitoring dozens of millisecond pulsars simultaneously, have become instruments for detecting gravitational waves directly. When gravitational waves from distant sources pass through our region of space, they cause tiny changes in the distances between Earth and the pulsars, showing up as correlated timing variations across multiple pulsars. This technique is sensitive to gravitational waves with much longer wavelengths than can be detected by ground-based instruments. The variety of pulsar rhythms spans an enormous range. Young pulsars typically rotate every few seconds, their powerful magnetic fields gradually slowing their rotation as energy is radiated away. Middle-aged pulsars may pulse once per second, while the fastest millisecond pulsars complete hundreds of rotations in a single second. Each category provides different insights into neutron star physics and evolution. Some pulsars exhibit complex timing behavior that reveals additional layers of physics. Intermittent pulsars switch on and off unpredictably, while others show gradual changes in pulse shape and intensity. These variations reflect changes in the magnetospheric processes that create the radio emission, providing laboratories for studying plasma physics under conditions impossible to recreate on Earth. The study of pulsar timing continues to yield surprises and discoveries. Recent observations have revealed pulsars with timing noise, random fluctuations that may result from turbulence in the neutron star's magnetosphere or changes in its internal structure. As we reach the end of our journey through the realm of neutron star music, we find ourselves contemplating objects that represent some of the most extreme physics in the universe while simultaneously providing us with tools to explore the cosmos with unprecedented precision. These gentle giants, despite their violent births and incredible densities, offer us a peaceful, rhythmic connection to the fundamental processes that govern reality itself. The radio telescopes that capture pulsar signals are among humanity's most sensitive listening devices. They can detect signals so faint that the total energy collected from all pulsars ever observed would not be enough to lift a feather. Yet within these whisper-quiet signals lies information about physics at the edge of our understanding. Each pulse carries data about the neutron star's magnetic field, its rotation, its motion through space, and even the structure of the interstellar medium through which the radio waves have traveled. Modern pulsar astronomy continues to reveal new wonders. Recent observations have found at least 2 neutron stars with a mass about twice the mass of the Sun, perhaps even more. These massive neutron stars challenge our understanding of how matter behaves at nuclear densities and provide crucial constraints on the equation of state of ultra-dense matter. The discovery of neutron star mergers through gravitational wave detections has opened another chapter in understanding these objects. The gravitational waves produced in a merger of 2 neutron stars provide rich information on the structure of these exotic objects, in which a mass roughly comparable to that of the Sun is squeezed into a sphere with a radius of about 6 miles. These cataclysmic events create conditions even more extreme than those inside individual neutron stars, forging heavy elements and providing laboratories for studying matter under the most intense conditions possible. The relationship between neutron stars and their environment continues to surprise astronomers. The magnetic fields channel matter surrounding the neutron star into light-emitting jets, much like those we see near some black holes. This similarity between neutron star and black hole phenomena suggests deep connections in how compact objects interact with their surroundings, despite their very different natures. Looking toward the future, next-generation radio telescopes promise to detect thousands of new pulsars, creating a galactic network of cosmic chronometers. These surveys will map the structure of our galaxy in 3 dimensions, trace the history of stellar formation and death, and perhaps detect exotic objects like pulsar black hole binary systems that could provide even more stringent tests of fundamental physics. The search for extraterrestrial intelligence has also adopted pulsar timing as a potential communication medium. The incredible precision and stability of millisecond pulsars could, in principle, be used to encode information in timing variations detectable across interstellar distances. Whether nature or intelligence might employ such methods remains an open question, but it illustrates the profound impact these objects have had on our thinking about communication and information in the cosmos. As space-based telescopes become more sophisticated, we are beginning to observe pulsars across the entire electromagnetic spectrum simultaneously. This comprehensive view reveals the full complexity of neutron star magnetospheres and the processes that create their multi-wavelength emissions. Future missions may even detect individual neutron star oscillations, opening up neutron star seismology as a new field of study. The gentle giants we have explored tonight represent more than scientific curiosities. They are natural laboratories where the laws of physics are tested under conditions we can never hope to recreate artificially. They are cosmic lighthouses guiding our understanding of space-time, gravity, and the fundamental nature of matter itself. And they are timekeepers, marking the passage of cosmic ages with precision that humbles our greatest technological achievements. And on that note, we conclude our peaceful exploration of neutron star symphonies. These cosmic musicians will continue their ancient songs long after our sun has faded, their radio pulses carrying messages about the deep physics of our universe to any who have the technology and patience to listen. Thank you for joining me on this journey through the realm of the gentle giants. Until next time, may your dreams be filled with the rhythmic pulse of cosmic lighthouses, guiding you through peaceful sleep toward another day of wonder and discovery.